I hope you've got over the shock of learning that light, an electromagnetic wave, behaves in some ways like a stream of particles, the photons, because I'm about to ask you to absorb another punch. I'm going to try to convince you that particles of ordinary matter, behave in some ways like waves. I don't mean by this that the particles bob up and down. They do that sometimes, of course, but that's not what I mean. I mean something much more fundamental. You'll pay a visit to this apparatus in this film, and I hope you'll be convinced by what it shows you that a particle can behave like a wave in a very deep-seated way. Maybe after the first punch, about the particle nature of light, the second, about the wave nature of particles, won't alarm you too much. If it doesn't, then you have something in common with Louis de Broglie. De Broglie suggested, back in 1923, that particles might behave like waves, and his suggestion grew out of his comparison of the way matter behaves with the way light behaves. He wrote that suggestion into a thesis he was submitting for a doctor's degree at the University of Paris. But if you find the waves of matter harder to take than the particles of light, then you're still in good company. De Broglie's examiners at the university were reluctant to give him a degree for such a fool idea. He got the degree all right, but only because Albert Einstein happened to be visiting Paris at the time and said, look, this isn't such a bad idea. Maybe it's even true. And then 4 years later, Davison and Germer in New York City and G.P. Thompson in Cambridge, England, described diffraction experiments they had done, quite independently of one another, showing that de Broglie's idea was right. Now, I think you've studied waves enough to remember that waves can be diffracted. Here, for example, you see waves coming up to the edge of a barrier and bending around behind it so that the barrier doesn't cast a sharp shadow. In fact, if you put something in the path of the waves which is no larger than the wavelength of the waves bend around from both sides and the thing casts no shadow. But if you shoot particles at something, for example, the droplets of paint from a spray gun, the particles either hit the thing or they don't, so that there's always a shadow. This way of casting a shadow, by spraying particles at a thing, is used in the modern electron microscope. Here's a small something that you want to examine in the microscope. You spray it with electrons, you put the beams of electrons through an electrostatic lens. The lens spreads those beams out. And you let them hit a fluorescent screen for a photographic plate so that you get an enlarged shadow of the thing. Here is a picture taken in an electron microscope of some of the tiny bits of matter that make up smoke. They look, as you might expect, like the shadows of little blocks. But the edges of the shadows don't look sharp. You see light and dark bands in them. The electrons making the picture don't seem to behave quite the way they should if they were simply particles like those drops of paint. Here you see a case of diffraction. Diffraction of particles, the electrons. In making those diffraction bands, the electrons are behaving like waves. You can get the same kind of shadow when you place an object, a razor blade, for example, in a beam of light. Now, I'll darken the room for a moment. Here's a small source of light, and when I line it up on that razor blade, you can see a shadow through the screen. Looking closely at that shadow, you see diffraction fringes. These fringes are very much like these other fringes made by electrons passing the edges of the smoke pits. So the electrons seem to be behaving like the light. And you might ask the question, are both the electrons and the light behaving like waves, or are they both behaving like particles? But you know the answer to that one. The bands in the diffracted light come from the interference of the light waves with one another. Looking for interference phenomena like this is the best way we know for finding out whether we are dealing with waves of any sort. So the electrons seem to be behaving like waves here. But it's worthwhile trying to find some way to check that idea. Now let me remind you of the diffraction of light by a ruled grating. Here's a thin sheet of plastic that has very fine ridges and furrows molded into it. Looking at them under a microscope, you see that they are arranged in straight parallel lines. The distance between them is very short, maybe about 20 times the wavelength of light. I have a sheet of that grating held flat under a piece of glass. When I shoot a beam of light at the grating, the ridges and furrows scatter the waves of light, and the scattered waves add up in just a few directions. In most directions, the scattered light cancels out. The ruled face reflects some of the beam back at an angle which equals the angle of incidence, but it also reflects some of the beam in other directions. And in those directions, the angle depends on the wavelength, the color of the light. So in those directions, the light is spread out into a spectrum, with the red light at the outer end of each spot and the blue light at the inner end. The wavelength of the light is shortest here and longest here. When I use only the red light, by putting a light filter in, you see what the grating does to light at the long wavelength end of the visible spectrum. When I shift filters and use only the blue light, you see that the diffracted spots all shift inward because the blue light has a shorter wavelength. Look at that shift again. Red light, blue light. Now, this suggests that if we want to look for the wave-like properties of matter, we might shoot a beam of matter at a grating and see how the matter bounces back. If it bounces back every which way, then that's just what we expect of particles. But if it bounces back in beams, then we suspect that the particles are behaving like waves. In order to get any useful answers, we have to design a grating with lines whose spacing is comparable with the wavelength we are looking for. But what wavelength are we looking for? In his original thesis, de Broglie made a brilliant suggestion. I've already reminded you that light comes in little bundles, the photons. Each photon has a momentum. That momentum shows up whenever the photon hits something, for example. And the momentum, P, of any one of the photons turns out to be given by h over lambda, where lambda is the wavelength of the light and h is Planck's constant. De Broglie's brilliant suggestion was that the same relation should hold for the matter waves. In other words, solving for lambda, you expect the wavelength to be given by h over p. This is sometimes called the de Broglie relation. Now let's get some numbers into this, using the units with which we are familiar, meters, kilograms, and seconds. In those units, Planck's constant h is about 10 to the minus 33. You see immediately that we're going to need a pretty small value of p to get a wavelength long enough to deal with. To make the momentum mv small, we want a small mass and a small velocity. An electron has a very small mass, about 10 to the minus 30 kilogram. If you accelerate the electron through a potential difference of 100 volts, you will give it a velocity of about 10 to the 7 meters per second. Then the momentum of the electron will be about 10 to the minus 23. Then de Broglie's relation says the wavelength of the electron will be about 10 to the minus 10 meter, which is about the size of an atom. So you want a grating with ridges and furrows spaced by about the diameter of an atom. Well, that sounds pretty difficult because, after all, the grating has to be made of matter, and matter comes in atoms. But the thing can be done. Here's a model of what one of the ridges on such a grating might look like. The atoms make little humps along the ridge. And when I put another ridge next to it, spaced by the diameter of an atom, the spacing of the humps along the ridges is as big as the spacing between the ridges. But when I've added many lines of atoms, you see that I've just made another sort of grating. Little humps regularly arranged in a plane. It's a different sort of grating from a simple line grating, but it's a grating all right. That grating is the regular arrangement of atoms on the surface of a crystal, and it's already made for you by the crystal, with just the right spacing to do an experiment with electrons. With a piece of plastic ruled with lines in two directions, like this graph paper, I could do the same experiment with light, if the spacings in that grating were comparable with the wavelength of light. Actually, I can get the same result by taking one of the light gratings with lines ruled in this direction and put on top of it a second with lines ruled in this direction. I've done this here, and when I shoot a beam of light at this grating, I get a symmetrical array of streaks. You'd expect that one of the gratings, working separately, would give you streaks in this direction, and the other would give you these streaks, but the crossed grating gives you these additional beams, making a square pattern. Now let me use those light filters again to show you what happens to the pattern at different wavelengths. Here's what the pattern looks like when I pass only the red light. When I shift to the filter that passes only the blue light, the pattern keeps its shape, but shrinks toward the center. I'll switch them again. Here's the red, the longer wavelengths. Here's the blue, the shorter wavelengths. Short, long. Now you know what you might look for when we accelerate a beam of electrons by about 100 volts and bounce it off the surface of a crystal. If the electrons are behaving like waves, we expect them to bounce off in beams which make a regular array of spots, and when we increase the accelerating voltage, so that we increase the energy and the momentum of the electrons and shorten their wavelength, we expect the pattern to shrink, like this. And now you're going to visit Dr. Lester Germer at Bell Telephone Laboratories, who has this experiment with electrons all set up. In his researches, Dr. Germer uses an apparatus in which he shoots electrons out of an electron gun. They go through a tube, bounce off a crystal, and come back and hit a fluorescent screen and make spots on it. Dr. Germer is the man who collaborated with Dr. Davison in the earliest experiments that showed the wave nature of matter, 35 years ago.
This is the apparatus which has just been described. I use it to study the arrangement of atoms on the surface of a crystal. This is an electron gun. Electrons come from this gun and are brought together into a narrow beam. This beam strikes the surface of a crystal. Some of the electrons of this beam are bounced off from the surface of the crystal at various angles and reach a fluorescent screen. they show on the screen as bright spots. From the positions of these spots, we know the angles through which these electrons were scattered, and from these angles we can work out the arrangement of the topmost layer of atoms on this crystal surface. In order to see the diffraction pattern made up of these electrons, we must turn off the lights. These switches control the voltages in the electron gun and bring these electrons into a sharp beam. We can now see the diffraction pattern which these electrons make on the fluorescent screen. This pattern was made by electrons having a speed corresponding to 40 volts. It is a symmetrical pattern, has the symmetry of the top layer of atoms of the crystal surface. Now I shall increase the voltage to 47. The pattern shrinks. I decrease the voltage, the pattern gets bigger again. I'm changing the voltage back and forth between 40 and 47. The pattern expands and shrinks. We're using only this small range of voltages because if we go to larger voltages, there are some subsidiary effects which we do not wish to show. The ratio between the sizes of these two patterns is the ratio of the square roots of these two numbers, 40 and 47. This is because the energy of the electrons varies directly with the electron voltage, and the momentum varies with the square root of the voltage. Correspondingly, the wavelength varies inversely with the square root of the voltage. I'm changing the pattern back to 40 volts now. The pattern is bigger again. And now again back to 47 volts with a smaller pattern. I could calculate the wavelength by finding the angles of the beams from the positions of the spots on the screen and by knowing the spacings of the atoms in the crystal. And this, of course, we do now. This calculation of electron wavelengths is like what Dr. Davison and I did 35 years ago. But our apparatus was not as convenient as this one. We couldn't see diffraction spots on a fluorescent screen. The old tube, which we had at that time, I now have in my office. This is one of our first experimental tubes. We detected reflected electrons by moving a collector around inside this can. How it works is best shown in a sketch. And I have here a sketch of the very first tube which was used. This is the sketch. This is the electron gun. It's the hot filament. The electron beam is defined by these pinholes. The beam hits the surface of a crystal. This is a box which can be moved around to different angles, and we can read the current at different angles just by tipping the whole apparatus. This box moves around under gravity as you tip the tube. Here is such a tube. The gun and the crystal and the collecting box are within this metal chamber and can't be seen. But as you turn the tube, this pointer moves around and it registers the angle of the collecting box. So we can measure the current to this collecting box at different angles. In one experiment, we got a result like this. This is a plot of the current to the box as a function of angle. This is the current. This is the angle of the box. There's a strong current coming straight back. We don't measure at angles less than 20 degrees. But from 20 degrees, with increasing angle, the current is decreasing. Then it comes to a new maximum out here at about 53 degrees. Then the current decreases again. If we had had a fluorescent screen, this peak at about 53 degrees would be recognized by a sharp spot on the fluorescent screen. This is a pretty tedious way of observing intensity maxima. It is very much more laborious than our present method of using a fluorescent screen. Originally, we were not looking for confirmation of de Broglie's theory of matter waves. We were doing these experiments before we had ever heard of de Broglie's theory. But as soon as de Broglie's theory came to our knowledge, we checked it against the positions and voltages at which our diffraction beams came out, and we found that they checked quite well. After finding the first few sharp beams, we made an extensive exploration and found that there were many diffraction beams and that they checked the de Broglie theory quite thoroughly and extensively. This was the first experiment in which electron diffraction was observed.
The experiment that Dr. Germer has just described to you is sometimes called the Davison-Germer experiment. Now let me describe to you the experiment that G.P. Thomson did in Cambridge, England, at about the same time. Thomson shot a beam of electrons at higher voltages right through a thin gold foil and examined the beams coming out the other side. Now Thomson's gold foil was made of very many tiny crystals, not just one. If we represented one of Thomson's crystals by this square grating, we would have to represent his gold foil by a great many such gratings turned every which way. Thomson's beam, narrow though it was broad enough to hit lots of them. Now I can use my square grating and a beam of light to prepare you to understand what he saw. One of the little crystals might give a set of beams like this, and another a set of the same beams, but all turned in a different direction, and so on. Well, from the whole collection of little crystals, you'd expect the diffracted beams to make the pattern that I get when I whirl this grating around. And here's the sort of pattern that Thomson actually got when a beam of electrons was diffracted by passing through a thin foil. Don't be disturbed by the fact that this pattern is made by transmitted electrons, not by reflected electrons. A transparent grating gives you just as good a diffraction pattern for the light that goes through as for the light that reflects. Of course, in Thomson's experiment, the electrons going through each crystal are scattered by layer after layer of atoms, not only the layer at the surface. But that just means that each electron is scattered by a three-dimensional grating instead of a two-dimensional grating. A three-dimensional grating diffracts a beam of waves in definite directions too. Indeed, light going through a crystal or through a foil made of many little crystals is diffracted that way whenever the light has a short enough wavelength, a wavelength comparable with the spacing between the atoms in the crystals. X-rays are light with that kind of wavelengths. Here is a photograph taken by a beam of X-rays shot through a metal foil, the same metal foil that was used for making the other picture that I showed you, taken with the beam of electrons. Comparing those two photographs, you see how alike they are. The electron photograph, the X-ray photograph. The spacings of the circles is the same in both of them. I find this a very convincing proof myself that a beam of X-rays and a beam of moving electrons have something in common, that they both have a wave-like property. The photographs aren't exactly alike. For one thing, the relative intensities of the circles aren't the same. After all, X-rays and electrons aren't exactly alike. X-rays are X-rays, and electrons are electrons, and the atoms in the foil scatter X-rays and electrons with different intensities. But both have a wave-like property, and the laws governing the directions in which they are scattered are the same. Now, de Broglie wasn't talking especially about electrons when he made his suggestion. He thought all particles of matter might behave like waves. And soon after the electron experiments, people devised experiments to show that de Broglie's prediction was correct for other bits of matter too. Here is a curve obtained by Esteban and Stern, working in Hamburg in 1929, with beams of helium atoms. They squirted a jet of helium atoms at the surface of a lithium fluoride crystal. Here is the beam of helium atoms reflected at an angle equal to the angle of incidence, and on either side of this, they found these beams of diffracted helium atoms. The wave-like properties of neutrons also show up when they are diffracted from crystals, whenever the momentum of the neutrons gives them suitable wavelengths. Here are pictures made by beams diffracted by a crystal of sodium chloride, a crystal of common salt. The picture on the left was made by X-rays. That on the right was made by neutrons. Today, the wave-like behavior of material particles is well established. Indeed, it forms a foundation for our way of understanding matter. The behavior of individual atoms and the ways they join to form molecules defied explanation until the wave-like nature of their electrons and nuclei were discovered. Nowadays, atoms and molecules are pretty well understood, but an account of that would need a film all its own. And the fact, which Germer helped to discover, that a beam of particles behaves like a beam of waves with the wavelengths de Broglie predicted, is used in countless researches. Here Germer is really turning the Davison-Germer experiment upside down. Instead of using the reflection from crystals to prove that electrons behave like waves, he uses their reflection today with confidence that the electrons will behave like waves. Since he can trust it, he uses it to find out more about the arrangements of atoms that are reflecting the electrons.
No?
6 times 10 to minus 7.
I'll do a little more. No?
Coming up slowly. 7 more.
That's enough.
8 times 10 to minus 7.
You see a spot develop?